So we'll go ahead and get started. So today we're going to be talking about RTXGI. This is the new lighting technique that we're using for global illumination in Unity. So this is a collaboration between NVIDIA and Unity, bringing real-time realistic lighting to Unity's high-definition render pipeline, or HDRP, in an artist-friendly way with RTXGI. This is global illumination that runs everywhere and benefits from hardware acceleration on NVIDIA RTX GPUs. So here's an outline of what we'll be covering today. First, I'm going to go over ray tracing and light theory, so we're all on the same page with the theory that underlies RTXGI. Then I'll explain a little bit about how RTXGI works using pictures, and then Kuba will show you a live demo of RTXGI in the Unity editor. And so we'll end with some specific advice for how to construct and light scenes in Unity for ray tracing and RTXGI, and show some results on demo scenes. So, ray tracing. So this is a pretty simple scene setup. There's a light at the top, which I'll call an emitter. It's a simple box geometry with a yellow wall on the left, a gray sphere on the floor, and then a camera view. And so the diagram is showing light from the emitter being cast in all directions, and it hits the yellow wall on the left and bounces yellow light towards the camera, and it hits the gray sphere on the bottom and bounces gray light towards the camera. And this is how we see color in real life. This is actual light transport, and this is what, when we render it, we call direct light. So because the gray sphere is on the ground, it casts a shadow, and so what that means is that it blocks light from the emitter that would have hit the ground. And this is what we call a direct shadow, because the sphere is blocking visibility directly from the emitter to the ground. So shadows have historically been computed with shadow maps. But now that we have ray tracing can produce perfectly sharp point light shadows and correct soft area light shadows in real time. So, global illumination. Realistic lighting requires not just direct light, but also indirect light. This is bounced light that is scattered off of multiple objects, possibly before hitting the camera. And this accounts for phenomena like mirror reflection, glossy reflection, diffuse interreflection, which you'll see a lot of in today's talk, and caustics, refraction, like you name it. All of these lighting phenomena are due to multiple bounces of light coming from the emitter and hitting the camera. I talked about direct shadows in the previous slide. There are also indirect shadows. This is when an object blocks indirect light that would have hit the camera. This is also known as ambient occlusion. So you can see an example of this on the left. The red X here on the left is blocking what would have been, is creating an indirect shadow from the ball, from that reflected light from the blue wall. So the highest quality way to compute global illumination is with ray tracing. This is how you render movies, everything with offline rendering. So you probably know about light maps, which is how most games handled indirect lighting until now. Light maps and light probes are ray traced pre-baked, so it's before you actually run the game in real time. But now that ray tracing can run in real time, we can replace these baked light maps and light probes with dynamic lighting. So I'll talk a little bit about how that works in Unity. So ray tracing in Unity provides a key advantage to creators, and this is because it allows developers to make and dynamically alter content in real time that looks photorealistic. For maximum photorealism, it uses ray tracing to provide reflections, like I mentioned earlier, and accurate dynamic computations for global lighting. So some key elements here. Ray tracing is added to Unity with a plug-and-play architecture. So what that means is that you can mix and match different ray trace effects to get shadows, reflections, refractions, what have you. And you can mix and match them also with rasterized effects. So it means that you have full flexibility in creating the effect that you want in whatever scene or game that you're trying to set up. And in addition, Unity also exposes an additional layer on top of an additional layer of ray tracing on top of what's already implemented in Unity, so that then you can implement your own ray traced effects on top of what's available without having to worry about the underlying hardware API or the underlying hardware or the ray tracing API that you're using. But all of this is available in the Unity 2019.3 preview. And on NVIDIA RTX GPUs, based on a new Turing architecture, all of these ray tracing effects are accelerated, so you can use more of them, and you can use them at higher quality. So this is the full lineup of NVIDIA RTX GPUs, And so the ray tracing performance scales across this entire lineup, from RTX 2060 all the way up to Titan RTX. To demonstrate that, let's just do a little back-of-the-envelope computation here. We'll pick one of the sort of mid-range ones here, the 2070 Super. And so say you want to ray trace your content in 4K at 120 hertz. Oh, sorry about that. Let's say you want to ray trace your content in 4K at 120 hertz. So if you want ray traced reflections, ray traced shadows, and using RTXGI, then you have 8 million reflection rays at 1 per pixel. You have 32 million shadow rays at 4 per pixel. Using RTXGI, you have 4,000 samples with 256 rays per each sample, and then 4 shadow rays for each of those, all at 120 FPS. So you multiply all of that together, and you get, roughly, that comes out to 6 gigaраys per second. The RTX 2070 Super is capable of 7 gigaраys per second at peak ray tracing throughput. Now, it's important to note here, this is theoretical throughput of ray tracing. Obviously, the actual performance you're going to get is going to be dependent on your scene because you have to shade all of those rays, and the shading cost is going to be dependent on the material model you're evaluating. So in our actual research code, we tend not to push things quite so high. But it shows you that the horsepower is available on the GPU for doing ray tracing in real time. So now we'll talk about RTXGI and what it's useful for and how it works. So why do you want RTXGI? Well, RTXGI is going to completely change workflow around lighting. If you use RTXGI in Unity, then you get immediate lighting feedback on all platforms where the high-definition render pipeline runs. So what this means is, if you move an object or you move a light, the lighting changes and the GI updates instantly. Not in 5 minutes, not in 20 minutes, but instantly. You don't have to redo parametrization, you don't have to try to fix up corners or sort of retune things. There's almost no light or shadow leaking using RTXGI, even with no tuning. And later in the talk, we'll go into how to tune it for maximum image quality on top of that. So here are some of the lighting effects that you'll get with RTXGI. I described earlier how bounce lighting in a scene, indirect light, creates all of these effects. So there are more phenomena computed by RTXGI than are up here on this slide. But here are 4 of the major effects. So let's take emissive shadows, for example. So for emissive shadows, what that means is that if you have, say, a large glowing object, like a bonfire or something, that will, with RTXGI, that will act as a true light source. So it will cast indirect light, and you'll get indirect shadows off of that emissive object for free. It doesn't have to be evaluated as part of your light loop. It's emissive, so it just gets evaluated normally in the material, and RTXGI will give you indirect lighting. So having gone over a bit of what you get with RTXGI, I'll describe briefly how it works. So RTXGI is a probe-based technique, and I've visualized the probes on this slide. Normally, of course, they wouldn't be visible. And so you'll notice that all of these probes are sort of this sort of light orangish color, and that's because most of the indirect light in the scene is orange colored because of those walls. So the probes are updated every frame using ray tracing, and so rays are traced from the probes along this line, this ray which I've colored orange to show the color of the light. And when they hit a point in the scene, that point is lit with direct light, which I'm showing with this white arrow here. And then that value is stored in the probe to provide indirect bounce lighting in the scene. So that's one bounce of global illumination. But actually, you get multiple bounces of global illumination because when this ray shot from the probe hits the scene, that point is shaded with the existing probes. And so once that happens once, you get 2 bounces, then every frame 3 bounces, and that converges towards what would be the correct infinite bounce lighting solution that you would see in a fully path traced scene. So one thing you'll look at here, one thing you'll notice if you look here is, so these probes are completely dark. That doesn't seem correct. But actually, if you look at where they are, these probes are sticking out of this wall. They are inside the geometry. They don't see any light, so it is correct for them to be dark. But the other thing that's interesting is that there's no leaking of that darkness onto this wall. There's no sort of shadow leakage from these probes. And that's because RTXGI correctly removes these probes from the shading computation when you render the scene from the point of view of the camera. But it would still be nice to use those probes for lighting because the more samples, the better. And so this is why RTXGI ships with a probe optimizer. And what this does is it dynamically adjusts the probes over any geometry that you flagged as static so that you get more use out of the probes for lighting the scene in real time. And so you can see all of the probes that used to be in the wall are now adjusted outside and are being usefully used for lighting computation. But actually, because we have ray tracing, we can do even more. So there's this sort of big dark spot in the frame here. That's actually a mirror. And so we have ray tracing, so we can give you real mirror reflections. And one thing you'll notice if you look in this mirror reflection is that we have these sort of spheres up here that are being reflected in the mirror. Those are also glossy, but they're dark. So we're not getting any what are called second-order reflections. This would be the light reflected from this sphere to the mirror and then back to the camera. And so you could compute the second-order reflections with ray tracing, but it's even more performant to use RTXGI to approximate the second-order reflections. Or if you wanted to ray trace them, you could approximate the third or fourth-order reflections. And this gives you the sort of a full, like, multi-bounce, not only diffuse reflection, but glossy reflection in your scene. And this is approaching the complete lighting solution you'll get using RTXGI with Unity. All right, so that's so much for intro. I'll hand it over to Kuba, who's going to give you a live demo in the editor. Take it away.
Thanks. Give me just a second. I need to switch the display settings. So I'm going to show you two projects. The first one is the Shanghai Streets project from one of the icons pack that Unity was collaborating on. This is a scene that's an outdoor scene that is made to be used on lower power devices. Basically, we'll try to light it here real time. This is the extent of the scene that you can see. Right now it's only lit with the HDRI. You can see that once I kill it, it goes black. Once I bring it back, it goes brighter. But you could ask, well, how is this actually lit right now? So if we disable RTXGI, this is how it would look if it was only lit via the default ambient probe and reflection probe. So the default ambient probe, the only thing it sees is the sky. So you can see that in all the alleyways there's plenty of light because that surface, for example, directly sees the bright area in there in the skybox. And enabling RTXGI gives us this nice occlusion in alleyways. Let's see where are the probes actually placed. So right now we're running at a pretty low resolution of just 10 by 5 by 10 probes. You can see here we have a volume of that many probes, and the volume extents are wrapping the entire scene. But we easily have headway on this machine to bump it up to get higher quality, and we can bump it up even further here when it comes to the amount of rays that we will shoot per probe in each frame. Now let's take a look at some directional lighting. So we added this sunlight coming from there. Let's take a look at the street level, at what does it give us. So here you can see that the direct light is hitting that brick wall. And here on the street, you're getting pretty nice red bounce from that light. And if we disable PGI and enable again, let's take a look at lighting only view. So here we're removing all the base textures and only showing the lighting output so that you can appreciate that part of it a bit more. So let's take the light and rotate it a bit. And see how the bounce changes. Now, the question is, how time-consuming is it to set it up? Well, actually, in this case, it's not at all. The only thing we did was to bring the prefab in that contains already the script that schedules all the tracing. And it contains a probe volume component where you can control the resolution. And also it has controls for the size. So you can see here that if I change the size to something small, right now the volume only covers a very small part of the scene and the lighting is broken and the rest. If I undo and I would size the volume correctly, then the lighting gets fixed. Now, do we need to manually adjust any probes? No, as Xander mentioned before, all the visibility information that is stored in probes that you can actually check out here, all that information that's stored in those probes allows us to not bother too much about where the probes are placed. Which also means that not only we can set it up really quickly, but we can do any modifications to geometry, like for example, moving this building here and not move any probes. All of this updates instantly. Now, what is lagging behind a bit is multiple bounces. As Xander mentioned before, since we're using the results from the previous computation when tracing against geometry, of course it takes a tiny bit of time to propagate the lighting, but even that for slow enough changes is not really noticeable. Now let's switch to the other project that we have ready. This is an example of an indoor scene. It's from the VFX demo from GDC. And in here we have a bunch of lights set up. Let's take a look actually at what do we have in the probes themselves. Just make them a bit smaller. You can see that there's actually quite a decent amount of bounced light in here. I'm gonna break it down for you a bit so that you can see which part of the final frame is coming from where. So if we just take a look at lighting only, this is all the lighting that we're getting on opaque surfaces. Then if we will turn off indirect actually lights quite a big part of even that small corner. Now the rest of the lighting comes from those monitors. They're set up actually in in a dual manner, if you will. There's both the PC screens that are just an emissive material. So whenever for our probes, whenever we're shooting rays, so if we take a look at the probes again, those probes that are closer to those screens have a pretty high chance of hitting those screens and propagating that lighting further. So that's what happens here. Let's just try to adjust the lighting. Now you'll see that when I adjust this, not all the lighting changes. That's because we also have some lights set up to light volumetrics in a direct way. Let's just turn that off for a second, just so that we can isolate it a bit. So this is all the lighting that we're getting from the emissive surfaces that are in that scene. And that means no additional shading cost. And you're getting, as Sander mentioned before, indirect shadows from those probes. One thing is actually using it fully real-time on your users' devices. But the other way you could use it is actually to have an instant feedback in the editor and then store the result for using in the player. Right now in this prototype, we're supporting just one volume, but concurrently we're working on supporting multiple volumes so that for different areas you can decide on the resolutions, on update rates, you can pause the different volumes so that you can easily scale it to bigger scenes. But as you could see in that outdoor scene, even for a reasonably sized small city block, it works just fine. And there's a lot of headroom even on this laptop for casting many more rays. And a lot of headroom for optimization for us as well. Now I'll hand it back to Sander. So we did both of those.
She can present it.
Oh, yeah, sorry. Just bring that. Just a second. Okay. Come on, PowerPoint. Yeah. Okay. Sorry, we're back.
All right. Thanks, Kuba.
Sure thing.
All right, so for the rest of the talk, I'm going to cover a little bit of ray tracing advice for artists. This is advice for making your scenes be beautiful and performant using RTXGI. So the first thing I want to talk about is volume placement. So RTXGI computes global illumination, multiple bounces of light. This means that you get a benefit from having probes everywhere, even in places where the player can't see, because then lighting can propagate through those places to places where the player can see for more realistic lighting. So what that means is you want to basically have your volume big enough to encompass your entire scene. And so there are some other guidelines here. I won't go through all of them. But basically the takeaway from this slide is when you're initializing that probe volume, just like Kuba was doing, you want to make sure that not only is it big enough to encompass your scene, but you have enough probes in there to get a good sampling rate across, spatially across your scene. So probes roughly, every 1 to 2 meters for human scale scenes, and you can get away with even larger spacing on sort of larger level size scenes. So now talk a little bit about tuning the volume. So the most important control for tuning the volume is what we call the self-shadow bias. This is the bias that controls whether or not a probe shades the point that it thinks it can see or not. And if you increase this self-shadow bias, you can get rid of any small lingering light leaks in sharp corners that might be there. And if you can get away with it lower, then it creates more contrast in the lighting. So here's what that looks like. So this is with the self-shadow bias off. And what you can see is you get this really ugly result from the GI because there's sort of the visibility is being sampled directly at the point where the mean distance result is sort of has its mean. So you get this weird sort of pattern, and you can see some of it over here too. This is with self-shadow bias that's too high. So you can see that all of those sort of weird leaking results are gone. But the lighting everywhere else looks really flat. We've lost all of that sort of nice sort of ambient occlusion detail that was on the sort of edge of the roof here, and then also back here on this wall. So this is with correct self-shadow bias. So you can see we've gotten back this ambient occlusion detail in on the roof and on this wall, and the result back here is correctly dark, as it should be also. So You can also rely on the optimizer, as I showed earlier, to improve coverage and get sort of more lighting samples in your scene. You'll also be able to optionally move the probes if you need to, but this is sort of maybe around your hero object, but this is sort of rare. You shouldn't need to use this for your normal workflow. So I'll talk a little bit about geometry. So again, real light bouncing, realistic global illumination. You want to make walls with real thickness, and I'll show you an example of why. So this is a sort of simple scene that illustrates this concept. There's a closed box, that's what this is, with a completely closed room, so dark on the left, and a room with one open door on the right. And there's a wall here that divides the two of them. We're going to look at it from the point of view of this camera. So all the walls here are infinitely thin. So if you look at this, you'll see that on the wall that divides, oh, it's very dark. On the wall that divides the two scenes, there are these sort of shadowing artifacts due to the fact that this wall is infinitely thin. And so I'll circle them a little so you can see them a little bit better. And so if you make the wall, thanks, Kuba.
It did nothing.
It'll be easier to see afterwards. But so if you make the walls properly have actual thickness, then the lighting computation proceeds as it should, and those artifacts go away. And in fact, the illumination, generally even in the rest of the scene, improves also. So here's the final view with correctly thick walls. And so you get no artifacts on the dividing wall, correct ambient occlusion in the corner, and then sort of powerful bounce lighting on the ceiling from the outside as you should. And so here are some other notes for optimizing your geometry for quality. Using single-sided geometry is best because I've been talking about the probe optimizer that will adjust the probes. That optimizer relies on back faces and static geometry to be able to adjust probes through walls efficiently. And I'll talk a little about this a little bit more later, but larger emissives, like Kuba was showing you lighting from in the demo, having larger ones will look a lot better than having smaller ones because they're easier to sample with ray tracing. All right. Now, performance. This may be the most important piece of advice in the talk. And the reason is because the other advice that I'm giving you will help improve image quality with RTXGI. But this slide will help improve performance not only with RTXGI, but with any technique that uses ray tracing at all. So basically, what all of these bullet points derive from is the fact that to accelerate ray tracing, the API will divide your geometry spatially. Basically, it will create bounding boxes around it. So just to take an example, say you have a triangle that is really long and thin. The bounding box, axis-oriented, that you would have to create around that triangle has high volume relative to the actual surface area of the triangle. What that means is that a lot of rays will hit the bounding box and not a lot of rays will hit the triangle, and this is bad for performance. So visually, what does that look like? This is bad geometry. These triangles are huge relative to all the other triangles in the scene. There are triangle fans up here. All of these really long, thin triangles share a vertex. There are more triangle fans here. This is exactly what you don't want. This leads to bad ray tracing performance. This, by contrast, is good geometry. So if you look at the floor here, all the triangles are laid out very neatly in this grid-like pattern. They're all exactly the same size. There are no triangle fans or sort of enormous triangles bucking the curve. So this is good geometry for ray tracing performance. All right, so a little bit about lighting. In the past, without real-time global illumination, it's easy to fall back on overlighting a scene by placing a lot of direct lights to make up for the light that's lost in bounce lighting. You no longer have to do this. In a realistic scene, about 25 to 50% of the light should be coming from the indirect bounce lighting. And so this has some interesting implications. What it means is, there are some scenes that you could light using just the sky, or just the sky with one or two lights pointing at certain places where you need more light. And so, you want to let when you're lighting a scene with either the sky or like one of these big directional lights, you want to let the light pick up the color for you, pick up the color of the indirect bounce. So color the materials and keep the light neutral, or color the light and keep the materials neutral. So this is a scene that's from the demo that Kuba showed you. And I want you to see right here this really nice sort of red bounce lighting that we're getting from the opposite wall. And so this is white light coming into the scene and giving us red bounce lighting from materials. And so this scene looks really good because it's dominated by this red hue. So a little bit more on materials. So we showed a little bit of this in the demo using emissives to get zero-cost lights. And I'll show you a result of that, or another result of that in a second. But you want to favor sort of dominant hues when you're using this technique, because if you have sort of too many different saturated colors, they can interfere in ways that create gray bounce lighting and cancel each other out. One of my favorite examples of this is if you have green bounce light that reflects off of a red wall, that result is black. So you get no light, you get no indirect bounce light coming from that at all. So here's our Shanghai scene that Kuba showed earlier. And so this is sort of a exaggerated haunted house effect. But it's important to note that all of the lighting in this scene is coming from those emissive walls. There are no other lights in the scene. And so you can see sort of in the streets and around the sort of nooks and crannies of this scene here, there's a lot of light coming in through those emissive walls. And so this is something that you can leverage to create really realistic looking scenes using RTXGI. Okay, so I want to conclude with one, I think, really salient example showing the visual impact of this technique. This is a scene from our demo, and this has, as Kuba mentioned, this has the lights coming from the monitors, which are emissive. It has one spotlight. It has sort of volumetric fog and unity. But there's no bounce lighting here. This is that same scene with the bounce lighting from RTXGI. And so I'll flip back and forth a couple times so you can really see the difference. And so one thing that's important to note here is when we give these before and after images, we're not comparing to pre-baked solutions like light maps or light probes. And the reason for that is because this is a real-time GI solution. Just like Kuba showed in the demo, you can move any of these emissive surfaces or this light around, and the lighting updates in real time. So we're comparing to basically previous real-time lighting, which would have been basically only your direct light and your volumetrics and everything else that's set up in Unity. And so for reference, here's where the probes are in this scene. So this is similar to the volume that Kuba showed you earlier. And one reason I really like this scene is because it shows multiple different effects from Unity. You have sort of like a particle effect going on here. You have the volumetric fog. You have obviously the direct lighting and the emissive surfaces combined with bounce lighting and indirect effects that you get from RTXGI. And they look really, really good together. All right, thank you very much. We can take questions.
We have 2 microphones, one on each side, so please don't be shy and ask us anything.
Oh yeah, thanks for the talk. I'm particularly curious about using the editor enhancements of real-time editor workflows and then shipping to, static players without the RTX hardware. How does that compare to light mapping and pre-computed GI in terms of performance? Do you have any information on that?
Mm-hmm. The biggest benefit that you'll get from this is the amount of memory that is used. We can actually switch back to the demo. I'll do that in a second. But sampling itself is fairly cheap. It is more expensive than sampling just light probes because we also need to evaluate visibility. However, it works well on fairly low power devices. We still need to profile, across all the ranges, so stay tuned on that. But definitely the workflow where you bake out the data that you see is really powerful. And what is also actually quite neat. Let me just switch back and show you something directly in the editor.
And it's worth noting also that the update rate can scale across hardware. So if you do your development with instant updates, then you can sort of set the update rate lower for like lower performance hardware, or even fall back on a BXGI solution, which will sort of still be better than previous probes because it has the visibility information. So you still won't get those leaks, for example.
Yeah. So we're back in this scene, and you can take a look here that in this scene right now, we're using 12 megabytes for the ray tracing acceleration structure that you will not need. We're using that much memory for the trace output, and then the only thing that you will actually need on your device is this texture, 250 kilobytes, and this texture, 500. Now this is with the settings that I haven't bumped yet, but let's just bump it to what we had before. And now you can see that together it's 3 megabytes to light that scene. So when it comes, if you would compare that with lighting it with light maps, where it's not a big scene, but it has a really big surface area if you take into consideration all the elements in it. That would be a few 2K textures. So calculating that in the editor would take a while, even with the GPU progressive light mapper, and then actually shipping it to the devices would take much more memory. The other thing that's kind of on the optimization angle, if you would see what's actually in our acceleration structure, it's actually only those bigger pieces of geometry here that affect the bounce in a big way. Everything else, so all the detail that's sprinkled around, is just picking up indirect lighting without needing to be in the acceleration structure. So also depending on the hardware that you'll be running the editor in, you'll be able to dial it like this for edit time, so that in the beginning you can get the mood perfectly with really good performance, and if you really need everything in the acceleration structure to get bounce even from the small pieces, then you can add it and just let it bake out.
One more follow-up question. Is this only HT render pipeline, or is there planned support for everything?
Currently it is. But there's, at least for using the result that is static, there's nothing preventing it from being used in the universal render pipeline. So we'll definitely look into that. Yeah, we can see how that would be useful, so for sure.
All right, thank you.
Sure thing.